Welcome to the studio, Catalyst. I am Professor Kemi Balagan. Today, we are opening a new site on the 2026-2027 syllabus, strictly anchored to Topic 1CD, Objective Roman numeral 3, distinguish between pure and impure substances. You've walked into the lab today asking a very sharp question. Prof, where do the examiners hide the cracks when testing purity? To spot a crack, you must first know what a perfect wall looks like. A pure substance is a flawless architectural structure. Every single atom or molecule is identical, built exactly like a masonry wall, where every brick is perfectly uniform. Because every atom is exactly the same, the chemical bonds holding that lattice together are completely uniform. Every single bond in the structure requires the exact same amount of thermal energy to break apart. Look at this crystal lattice. Because the bond strengths are uniform, when we apply heat, the entire structure holds together. The instant the thermometer hits 0 degrees Celsius, every bond breaks at once. A pure substance melts at one single, sharply defined temperature. In chemistry, purity is strict structural perfection that dictates predictable, instantaneous thermal behavior. So what happens when we compromise the site? An impurity is a wrong-sized brick introduced into our perfect architecture. Watch the diagram. We insert this giant mismatched red block into our perfect blue lattice. The surrounding blue blocks are instantly forced out of alignment. They warp, they bend, and the tight structural integrity of the solid breaks down. Notice how the warped areas are pulsing. We have introduced areas of unequal bond strength. Some connections are stretched thin and weak, while others remain rigid. When we apply heat to this compromised structure, those stretched, weakened bonds will snap much earlier than the rigid ones. The lattice no longer fails all at once. The solid begins to collapse slowly over a wider span of temperatures. We term this a melting range. A pure solid surrenders to heat instantly at a single point. An impure solid staggers, melting gradually as the heat slowly breaks down the differing bond strengths over time. An impurity is an architectural flaw. It destroys the uniformity of the lattice, making the transition from solid to liquid a chaotic collapse rather than a sharp, instantaneous shift. Let's bring this abstract thermodynamics onto a Legos construction site. Look at this cross-section of a freshly built concrete block wall. Right in the middle tier, someone has shoved a piece of rotting, mismatched wood between the grate blocks. Catalyst, look at it with your lab eyes. Does that wood make the wall stronger, or does it create a glaring weak spot? Exactly, it's a weak spot. If a heavy load or external pressure is applied, which in our lab represents heat, that wall will immediately buckle exactly where the wood is located. The wood is our impurity. The concrete blocks are pure atoms. And that premature buckling under pressure, that is the melting point dropping. This gives us the first half of our thermodynamic rule. Impurities lower the melting point of a solid. In chemistry, we call this melting point depression. The weakened structure falls apart sooner, and because the rest of the concrete takes longer to fail, the collapse drags out over a wide temperature range. Heat always targets the weakest structural link first. Therefore, a flawed solid surrenders to heat at a much lower temperature than a perfect one. We must now examine why impurities exert opposing forces, driving melting points down in solids while pushing boiling points up in liquids. To answer that, we must look at the physical mechanics of boiling. For a liquid to become a gas, its molecules must physically travel to the surface and escape into the air. Look at this cross-section of a liquid system. We've added large, heavy, unreactive impurity particles. They gather at the surface, physically blocking the blue liquid molecules from escaping. With the exits blocked, the liquid requires significantly more thermal energy. The molecules vibrate violently, absorbing heat until they finally push past the gray particles. This gives us the second half of our thermodynamic rule. Impurities raise the boiling point of a liquid. We define this as boiling point elevation. The board sets traps here. Examiners know students memorize rules without understanding whether the impurity is breaking apart a solid lattice or blocking the exit route of a liquid. The physical state of matter dictates exactly how the impurity will interfere with the system's thermal behavior. Impurities are situational saboteurs. They weaken the internal walls of solids, but they barricade the exits of liquids. Let's test your foundation with a high-stakes lab mystery. I'm pulling a standard structural test directly from the question archive. This is UTME 2017, question 40. The presence of an impurity in a substance will cause the melting point to... Notice carefully, Catalyst. We are specifically evaluating the effect of an impurity on the melting point. Before you even glance at the options, answer this first principle question. Are we making the chemical bonds stronger, or are we creating a weak spot in the solid lattice? Think back to our Lagos brick wall. When we shoved that rotting wood into the concrete, what happened to the wall's integrity under pressure? Exactly. You've recognized that the wood creates a weak spot. A weak spot means the structural integrity breaks down much easier than a perfect wall. And if a solid structure breaks down easier, it requires less thermal energy, less heat to melt. We never rely on rote memorization to pass the board's exams. We deduce the correct path by interrogating the structural mechanics of the question. Your logic is solid. Since it requires less heat, the melting point drops. Option B, reduce, is the correct designation. But keep your lab eyes open. Look at option C, increase. That is the examiner's crack, a trap laid specifically for students who rush. The board includes that distractor because they know unprepared students confuse melting point depression with boiling point elevation. They want you to second-guess the mechanics. Apply the sharp logic. Impurities weaken solid structures, dropping the melting point, but they trap escaping liquids, forcing the boiling point up. Solid work, the catalyst. The foundation is set. Your mastery of this concept is confirmed. Now, return to the dashboard. To ensure the structural integrity of this concept, go to the studio and launch the Topic 1CD video, slide, and mastery quiz to move your chemistry progress bar to 100%. Maintain your focus on the structural mechanics of the molecular blueprint. No dulling, the catalyst.